Hello everyone, this is the recording for lecture 5, lighting 1. As we can see, this is the first lecture in our lighting. In this lecture, we're going to cover these topics. As we can see, these are more like introductory topics about lighting and more like to understand the basic concepts of lighting and basic terms. We're going to talk about the introduction, then we're going to talk about the most important terms in lighting that we're going to need later on for design. Then we're going to talk about something called reflectance and transmittance, then color, vision, and perception. So first, let's have a look at introduction about lighting and architecture. As we can see in these two images, these are two images of the same space, but the difference in between them is one of them having lighting from inside and the other one it has no light from inside, only lighting from outside. As we can see, the source of lighting and the color of lighting has a major impact on how we perceive the space. So as we can see, building design perception is affected by two things: the quality of the physical design, definitely in here. As we can see, this ceiling design has a major effect of how we perceive the space, how we see the space, and the quality of lighting for it. As we can see in here, because we have no lighting for the inside, then we can't see what we have down in the ceiling. We only can see the windows. As we can see in here also, we can't see the windows. So lighting source plays a major part on how we perceive a space, and actually the color of the light has a major part on it as well. Let's have a couple of examples of how the ancients, Greeks, ancient Egyptians used lighting techniques in their architectural design. Now let's have a look first thing about pyramid engravings. As we can see, these are examples of pyramid engravings they've done in ancient Egyptians. As we can see, these engravings are very shallow and they took into consideration the type of sunlight falling on it. As we know, the type of sky is in Egypt is clear sky, so the sunlight is very direct and very bright and clear. So they had to be measured to create these very dark shadows and make the drawings more prominent and more live. Now let's have a look at how the Greeks used lighting for their favor in architecture. Now the Greeks had a more of a less bright sun in Greece. The sun mostly was overcast, so they had to create something. The form has to have more depth, so it can create and make use of the less bright sky. So as we can see, they used a niche in here, and this niche it created the effect of we have a effect of this entrance, emphasizing the entrance. Also, as we can see, the sculptures they had to be more deep. As we can see, these were shallow in the Egyptian ones, and here they're more deep, and actually they're more like sculptures. They're not in engravings. So the first bright daylight, it's not sunlight, it's daylight actually, had to give them more, as we can see, depth to them when it falls on them. Now, if we actually used these sculptures in the Egyptian skylight, Egyptian sunlight, their detail is gonna be obscure. So we have to be careful when we are taking light into consideration. We have to be careful what type of skylight we are having, what type of light or daylight we are having in our site. So as we remember in acoustic design, we didn't design for quantity, we designed for quality. So the same thing applies for lighting design. Also lighting, we look for quality and not quantity. What do we mean by quantity? By quality? Well, quality depends, of course, to achieve a minimum required level of lighting in a space, and also to avoid certain issues that we face in lighting, for example, like glare issues or high brightness issues, which are going to have a look at later on in other lectures. So for us as architects, we can control two things. We can control the form of the building, and we can control how the light like falls on the form or actually enters the form, so it affects how the appearance of that building. So as we can see, the architect creates the visual environment by both molding the material and controlling the lighting. As we can see in these images, as we can see in this image, first thing, we see that they have certain openings in the roof and the ceiling. So they have an effect of how the ceiling looks like and also how the light falls on the walls and creates a like extension of the ceiling design. Also, as we can see in here, the shape of the building is much affected by the shadow falling on it. Also in this one in here, as we can see, we are having specified the same material for all over the walls, but how the form is actually affecting how light falling on it and creating like certain depths in some areas. Also, as we can see in this picture, it's very the importance of using electric lighting at night and how that using lighting at night affects like majorly affects the shape of the building. Now, if we look for the form of the building or the look of the building in the morning, it's going to look much differently than what we see now at night. This is because that at night it's much effective with electric lighting that we designed for. So far, as we said, architectural lighting much depends on the quality of lighting. So lighting must satisfy three major needs that are aesthetic, biological. So we were talking much in here about the aesthetic of the building and how lighting affects it. So we have to look for the aesthetic needs, biological needs. So we have to take into consideration like how we as humans, is the building satisfying our needs, our biological needs? Then lighting required to perform certain tasks. This is too important for interior spaces and the lighting level for interior spaces. So the design for lighting actually goes into three steps. So the first step we have to look for is the form of the building and the materials we are specifying. So this is what we actually discussed in these slides in here, that the form actually creates certain visuals in the building. Then after specifying that, this is much related to the form or actually the aesthetic part of the building. Then we're going to introduce some light to actually and like help us satisfy our biological and our activity needs. So we're going to introduce daylighting into our spaces. So daylighting, we're going to later on discuss how we're going to do that. So it's going to discuss how we want to introduce as much as possible like natural daylight into our spaces and try as much as possible to avoid electric daylight. Now, in some areas, in some spaces, we can't avoid, sometimes we need to add another extra electric lighting. So it's going to be the third step to cover what's uncovered in these two steps in here. So now let's understand the physics of light uh, before we go into further details about lighting and architecture. So as we can see, light is actually a type of electromagnetic energy. So this is, as we can see in here, this is the electromagnetic spectrum. And light consists of only a portion of it, as you can see in here. This is what we see. Now the infrared part and the ultraviolet part, we can't actually see them, but we can feel the infrared as heat. The ultraviolet affects us as humans in many certain like ways, but we can't see it as we can't see its colors. We can't visualize it. So in our design, we took this part into consideration, and the other parts are of least importance. Now, these are the most important light terms that we will need later on to actually know about and use. So we have something called luminous flux, and it's measured in lumen. We have something called efficacy, We have something called luminous intensity, which is measured in candle power and candelas. Then we have something called distribution pattern, candle power distribution graphs, illuminance, then brightness and luminance. So before I discuss each one of them in further detail, just have a look at them in here. So now luminous flux, from its term, it means the amount of total light coming out of a lamp. Now the efficacy is actually how efficient the amount of light coming out of a lamp and relatively to the power input into that lamp. The luminous intensity is actually discusses like the amount of light in certain directions. Now, in luminous flux, it's like the total light coming out of a lamp, but it doesn't matter in what direction the light is being scattered out of the lamp. Now, luminous intensity quantifies in certain direction, like the amount of light we are having in that direction. So it is much related to how wide the angle is of the lamp or how narrow it is, and also relies on the luminous flux as well. Now, distribution patterns is actually what determines the luminous intensity. This is how we represent the angle of light coming out of a lamp. So it's called distribution patterns, and it's represented in something called candle power distribution graphs. Now, illuminance, and we have brightness and luminance. Luminance is how much light is actually falling on a surface. And brightness and luminance is how much light is being reflected off the surface so we can see it or it reaches the other areas of a space. So as we discussed, the first thing, the luminous flux, so it is the supply of light. As we can see, it is measured in the unit of lumen. So luminous flux, as we can we can have this analogy. So this is the amount of total light coming out of a light source. And this is, as we can see in here, the number, actually the quantity of water gallons coming out of a water hose. Now, as we can see, light is, the amount of light is actually being emitted as a rate. So, okay, we're having, for example, 100 lumens getting out of this light source, but the lumens, they're actually the amount of light per a time period. So once you turn it off, it's going to stop. Okay. So luminous flux is the power in which light is emitted from a lamp. As we can see, it's measured in lumens. So as we can see in here, we have the different types of lamps. We have this incandescent light, we have this fluorescent light, and we have this high pressure sodium. Now, as we can see, each one of them has a different amount of light coming out of it. Now, incandescent, it has 1740 lumens and 7800 lumens coming out of the fluorescent, and high pressure sodium is 9500 lumens. Now, as we can see, these lamps all have 100-watt power, so it makes the comparison much easier. So as we can see, the incandescent produces the least amount of light, the least lumens. So as I introduced to you earlier, the term efficacy. So efficacy just describes the efficiency actually of the light source. For example, in here, the incandescent lamp, the fluorescent lamp, or this potassium high pressure sodium, lamp. Now, as we've seen from the previous slide, this one, while we are using 100 watt for each one of them, this one is producing the most light. So we can tell that this one is actually the most efficient. So to actually calculate the efficacy of a light, we just divide by the amount of light energy coming out of the lamp and divide it by the electric energy we put it inside the lamp. So if they all had 100-watt energy in, and each one of them had a different amount of lumens emitted. So for example, for the incandescent, if we want to calculate the efficacy, as we can see in here, We just divided 1740 lumens by the wattage of that lamp, and it's 17.4. So as we can see, the higher the number, the efficacy number, the more efficient it is. So in this example, the most efficient type is the high pressure sodium. Now let's talk about something called luminous intensity, or which is sometimes called candle power, and it's measured in the units candle power and candles. For our course, we are going to follow the SI system. So it's the metric system. So candles is the metric system. So as I discussed earlier, let's have a look at them. So as I discussed earlier, the luminous flux describes the total amount of light coming out of the source. Efficacy describes the relationship between the total amount of light produced or emitted in comparison to the energy in given to the lamp. Now let's talk about the light intensity in certain areas. For example, let's have a look at these two light types. Both of them, they have the same amount of luminous flux. They both produce in total 2000 lumens, as we can see in this one and this one. But as we can see in here, this light is more narrow, more what we call directional lighting. So definitely, if we are like squeezing in the same amount of light into a narrower area, we are going to have a more intense type of light. So this is what we are going to discuss in here, luminous intensity. So this was easy to predict from these two graphs. As we can see in here, like the total is 20 degrees in total, and this one is 110. It's a wider range. So we can tell that the intensity of light in here is higher. So in here, the measurement is 7,400. This is the intensity of light in any direction. And in here, it's 1,100. So as we can see, this is much more intense. This is like 7 times intense than that one. So to figure it out for any lamp source, we need to get something called distribution pattern. So this one will give us a more detailed idea how the light is being distributed. And there is something else we need to take into consideration, that usually the light is more intense in the center, and usually at the sides or at the edges, the light it has of least intensity. So this is can be detailed in these distribution patterns or distribution graphs. As we can see in this one describes that type of light, and this one describes this one. So we can see the range of 20 degrees is actually clear in here. So this is the edge of the 20, and here is the edge of the 20. So we can see that the highest intensity is actually in the middle. So in each direction, this is showing how in each direction, what's the intensity of light. So in the center, it's somehow 5,500 maybe, or 400 candle power. At the sides, it's of least intensity. Let's have a look at the other floodlight source. As we can see, it's of a wider angle. So it ranges between like the 55 to the 55 in here. So it's 110 in total. As we can see, it's almost the same intensity in between the 20 to 20. So from here to here, it's the same intensity. Then it fades in its intensity at the edges. But we can tell that in the center, it has least intensity than this one. This one is reaching above 5,000 candle power. This one is almost below 1,600, so it's more like 1,500, 1,100 maybe. Usually we can get these distribution graphs from the manufacturer. So if you want to specify a light, so you can get this graph along from the manufacturer you are getting the light from. Now let's talk about another important term in lighting, something called illuminance. So as I previously described it, it's the amount of light falling on a surface. So as we can see, its definition is the number of lumens falling on each square meter of a surface, definitely we can measure it by the area that the light is falling on. For example, in here, as we can see, this is a square meter area. So we are measuring in this square meter area the number of lumens falling on it, or foot candles. So the number of foot candles falling, the total number of lumens falling on a 1 meter square area is actually what we call lux. So for example, if this is a 1 meter square area, the number of lumens is going to represent the number of lux of the falling on that area. So as we can see, the closer the surface it is to the light source, the definitely the higher the number, and the further the surface from the light source, definitely is going to be the lower the number, because the same amount of lumen is going to be spread over a wider area. So also this makes sense. For example, if you want to read something, just bring the paper near the light source is going to be brighter. Just take it away from the light source, it's going to look least brightness. The other measuring unit is for lux is the foot candle that we represent sometimes with FC, but for this course we're going to use the lux. So 1 foot candle equals approximately 10 lux. Usually we can measure the lighting, falling lighting on any surface by instrument called the photometer. This is a picture of the photometer. So this is where you get the reading and where you press to get the reading. So you can specify what time you want to get the reading. This is actually the sensor, the light sensor. This is where you locate where you want to read the light falling on a surface, on this one. Now these days we can get similar. We can like instead of getting this tool, you can get an application on your phones, whether an Android or iPhone. You can look for something called like lux meter or light meter, and you can get the reading of lux from your phones. And somehow you can replace these ones, but definitely these ones are more sensitive and more accurate. So this is like how you can calculate the amount of lumens. So for example in here, so we know the amount of lumens falling on the surface area, and we know the surface area. So we want to get the lux value or foot candle value, so we can just divide the lumens over the square meter of the surface, and we can get the lux value. For example, we know that 80 lumens is falling on this table, and this table size is it's around 30 centimeters, so it's 0.3 meters. So as you can see here, the calculation is 80 lumens over zero point 0.3 times 0.3 is actually 0.09. So 80 lumens over 0.09, we're going to get 222 lux. Or you can calculate it using the foot candle. So it's 2 by 2 feet is 4 feet. So 80 over 4 feet is 20 foot candle. As we said before, 1 foot candle almost equals 10 lux, so it's almost similar, 200 lux. 220. Now, let's have a look at the last and very important terms in lighting. So we have something called illuminance, luminance, and brightness. So previously we've discussed illuminance. So what we said earlier, illuminance is actually the amount of light, whether in lux or foot candles, is the amount of light falling on the surface. And we can measure it with photometer. Now, this light is going to reflect off the surface, and this is how we perceive it, or actually see it. So when it reflects off the surface, it's going to enter our eyes. We're going to see the reflection. That's how we're going to see the object. So we have two things. It can be either quantified using a photometer, the amount of light being reflected off. So this is what we call luminance. Or we can this is much related to our perception, our eye perception, and we call it brightness. Now, luminance and brightness are almost the same thing. The main difference is that our eye interprets luminance in a different way sometimes, because it depends on many factors. So we can't actually quantify brightness just by measuring with a photometer. So we take into consideration the measurement of the photometer of the luminance. Then we take other factors so we can determine the brightness. So brightness relies on luminance and other factors. Luminance is the objective measurement of light reflected off a surface. So as we can see in here, we have the difference between brightness and luminance. So if you actually see, the main difference is the brightness is refers to the perception of human observer. So as I said earlier, it's much related to how I see, to my eye, how it perceives the lightness, the luminance reflection. And luminance, the actual is the to the objective measurement of the light meter. So it's the actual light being reflected off, the number of light being reflected off. So as we can see, the brightness, as we said earlier, it relies on luminance and other factors. So, okay, it relies on the object's actual luminance. It relies on the adaptation of the eye. Then it relies on something called the brightness of adjacent objects. So for us as human beings, we actually perceive the brightness of an object affected by two things: adaptation of our eye, how our eye pupils actually open or widen or tighten, and the brightness of adjacent objects. So the relationship between the brightness of the object perceived and the objects around it. Now, the luminance is much more objective, as we can see. It's related to the shape, the color of the object, the specularity, whether it's smooth or rough surface, the color reflectance of the objects. So these ones we can actually quantify them. These ones we have to actually understand how the human being eye is actually working. So this is a summary of all the terms and the units we covered in this part. So as we can see, we first discussed the luminous flux, and it's describing the amount of supply of light. So we can measure it according to the metric system using lumens. Then we have something called luminous intensity, which is, as we said, the amount of light in a certain direction, and we measure it using candelas or candle power. Then we have the illuminance, which is lux, how much light is falling on a surface. Then we have the luminance, how much light is being reflected off a surface. So it's candelas per meter square. Now let's talk about important interactions of light with the medium. So as far as we remember what we learned in acoustics, we had basic interactions. So it's much similar to light, but light has lesser interactions. So the most three basic interactions with the medium are absorption, reflection, and transmittance. So light first falls on the surface. Some of the light will be reflected, or maybe most of it, or maybe 0% of it. Then some of the light can be transmitted. Then wherever through transmission, sometimes some of the light is being actually absorbed in the medium, for example, the glazing. So let's have a look first about the reflectance, then we're going to talk about the transmittance. So as we can see, reflectance, we have three aspects of light reflection. We need to specify how much light is actually reflecting off the surface. So we call that specified by something called reflectance factor, RF. Then the manner how the light is being reflected off the surface, as we can see in here. So this is specular reflection. This is like a mirror. If it's perfectly reflected, it's gonna create a mirror. If it's diffused, it's reflect. It's gonna look something like this, like a rough surface. Then spectral selection. So as we learned earlier, light is actually portion of the spectrum, electromagnetic spectrum. So as we can see in here, how light is falling on a red apple, and we can see the color of the apple. So the reflectance of the apple is actually selecting only the red to be reflected off. And these also are examples of the reflectance factor. So as we can see, 10% is actually like 1.0.1. reflectance factor, and this is 0.9 reflectance factor. So it's like a percentage ranging from 0 to 1. So let's have a look at each one of them in more detail. So this is the reflectance factor, as I discussed earlier in here. So the reflectance factor is just how much light is being reflected off from the incident light falling on the surface. So it's just the percentage value. So it's never going to be above 100% definitely. So there is going to be between 0 and 1, and it's never going to be 0 and it's never going to be 1. For example, a white surface will have a reflectance value of 85%, 0.85, as we can see in here. And the black surface will actually emit some of the light, not too much, but some. So it's going to be a value of 5%, which is 0.05 reflectance factor. So, okay. Now let's talk about the manner of reflectance. So as I discussed earlier in this one here, we have two types, main types. We have specular reflection, diffuse reflection. Now specular reflection is the smoothly reflected type. So it requires to have a very smooth surface, and that the incident light will equal the angle of incidence of the light will equal the angle of reflection. So this is much similar to what we learned in acoustics. Then if the surface is actually rough, then the light will be scattered away and diffused, and we will call it diffuse reflection. Now sometimes we can have a mix of both, that the light, like the surface is slightly smooth, most of the light is being reflected in this manner, but some of the light is being diffused as well. So this is much related to the type of material of the surface. Now let's talk about the transmittance. So much similar to reflectance. So let's go back to the different types of interactions with the medium. So as we said, some of the light can be reflected, or maybe most of it, and some of the light will be transmitted. So the same manner we quantify how much light is being reflected, we were going to quantify the transmittance. So we have something called transmittance factor. So for example, in here, so transmittance factor is actually going to measure what percentage of incident light, of the light falling on the surface, is going to transmit through the medium. For example, in here, through the glass. So how much light is falling on the glass is going to pass through the glass to the other side. As we can see, the light is coming from the inside of the space and it's getting outside. So we can see it because the glass allows the light to travel from the inside to the outside. As we can see also in here, we have two types of glass. We have the clear glass and we have the frosted glass. Now, there is something you need to actually learn is that the clear glass and frosted glass, they both transmit the same amount of light. They have the same amount, the same transmittance factor. They both transmit 85% of the light, which is a 0.85 transmittance factor, meaning that, but the main difference is that clear glass is more of a straight specular transmittance, but the frosted glass is just scattering the transmittance into different directions, which is causing a blurred image of the original light on the other side. But at the end, the same amount of light is being transmitted, just the manner is different. Now let's talk about color. So as we've previously described it, is the spectral selection of reflection. So let's have a look earlier about at the electromagnetic spectrum here. So as we can see, this is the electromagnetic spectrum. We said that light consists only of a portion. Now light consists of different colors. So each color is represented by a different wavelength. So according to its wavelength, we're going to see it as a different color. So as we can see in here, to actually describe colors in more numerical and more details, We have something called spectral energy distribution diagram or spectral power distribution diagram, SED or SPD. These are the diagrams we are talking about. For example, the color blue is actually not pure blue, as we can see in here. It's actually a mix of a couple of colors. So in here, in this diagram, it's just the same. This is the range of the wavelength of the visible spectrum. So it ranges from red up to violet in here, according to the wavelength. So it just shows us the amount of each wavelength uh, like found in the light. For example, in the blue light, most of the wavelength is in the blue range, and some of it green, and some of it probably in the violet. But when you mix all of these colors, we get the color blue. The same thing applies for green. So it's not a pure, you can't just specify one wavelength for a color. It's usually a mix of more than one. So this is the green color, the green light, and this is the red. So most of the light is in the red area. Most of the light in here is in the orange area. And then pink is a mixture of red and yellow and blue, as we can see. And this is yellow. Most of it is the yellow, and some is green, and some is red. So now we understand what we mean by SED and SPD. Just represents uh, what uh, what what light colors are included in the light. So for example, this is used, for example, here to compare the white light of the natural daylight. So we have different times of the day with different shades or different, let's say, temperatures of daylight. So we have, for example, the direct noon sunlight, which is very intense at 12 p.m. And we have, for example, the north light, which is coming from the northern window, which is actually consisting of a reflection of light from the sky into the window, because there's no direct sunlight actually entering from that window, just reflections. So the color temperature or the color of each light is going to be slightly different. They are both white, but somehow you sometimes find that the light coming from the northern window is somehow bluish. So now let's have a look at the SED of each one of these lights. So this is the SED of the white light at noon time and direct sunlight. So as we can see, it's the amount of red, orange, yellow, green, blue. They're almost the same. Only there's a decrease in violet color. So as we all know, probably should know, that actually the white light is a mixture of all the colors together. So when you add all the lights together, you should get a white light. Any decrease in any of these lights is gonna create a different shade of white. So as we can see in the northern light, which we said is bluish, let's have a look at its SED. So as we can see, the red is almost the minimal light in it, and the maximum is in the blue range area. So this is why we see the color, the white of the northern light somehow bluish, because most of the wavelength is more intense at the blue light. So it consists of all the lights, but most of the light consisting of that color is in the blue range. So this is another representation of these SED diagrams with colors. So as we can see in here, this is the noontime daylight, clear sky daylight. So it's almost the same. Now, as we can see in here, this is the north sky daylight. So as we can see, we have an abrupt increase in the bluish range. So let's have a question for you. So what do you think? Do you think it is better if you are painting a drawing and you are using colors in that drawing? Is it better to locate that room facing south or facing north, according to the information we know so far and your ideas? So first, let's discuss both, as we know that the southern window introduces light with this SED, this SED. So it's more of the white colored light, and the northern window is this one, more bluish. But there's a problem is that this light in the southern window, for example, is not always this light color. For example, during early morning times and during afternoon times, the light will be at a different angle and coming from east and west, and maybe it's bluish and maybe more on the orange hue range. So, so the light color actually differs according to the time of the day on the southern window, while on the northern window, the light color will remain the same, only the amount of light will be different. So it's gonna stay bluish throughout the day because there's actually never a direct sunlight coming through that window, and it's always gonna be the reflected light coming from the sky. So this is why they prefer and they recommend that if you are using the, mixing and matching colors at different times of the day and you want to be consistent with what you are doing, so you need to use a more consistent, more constant color, white color. So the northern window will actually satisfy this. So it's gonna say the same thing but different amount, which is not gonna affect your mixing and how you see or view your painting. So this is why, as we can see, why is north light the ideal white light for painters. So this is actually the basic reason why the northern window is most preferred for painting and mixing colors and working on a project that needs colors. So now, so far, we learned that the color of a surface is due to two things. So it relies on the surface itself, the type, what color it's gonna reflect. So it's called the color of that surface, and it actually relies on another thing, which is the light falling on that surface, the color of that light falling on that surface. So as we can see in these three images, we're having the same space at different times of the day. So we have the same spectrally selective reflectance because it's the same materials each time, but the only difference is actually the spectral composition of the illumination. So each time this is maybe early morning time, so maybe the sun was in the east, so it looked more of a bluish hue, white. Now at noontime it was direct, so it was more white. Now at night or afternoon, so it's a little bluish as we can see coming from outside, so we are introducing now electric light. So as we can see, we are perceiving the color of space differently according to the light falling on it while it's the same space and the same colors. So the same diagrams can be representing the light of an object, for example. This is just to represent the light, the color being reflected off the object. So we first used it to describe the light itself, and this is gonna be used also for the reflectance of light from an object. So as we can see, for the red object, most of the reflected light is in the red range and orange range. Some of it is going to be in the other colors. So as we can see, each color is not actually a pure color. For example, when I say a red ball, it's not going to be only in the red area. It's not going to be only a line here. It's going to be all over the other colors, but most intensely in this. Most of the reflectance is going to be in this range. So it's gonna be almost like 10%, 5% reflectance of other colors, but around like almost 90% of this color. So as we can see in here, when we are having, for example, a red surface, if we are having a white light falling on it, it's gonna reflect only this range. It's gonna reflect all these lights. So it's gonna reflect the red plus all these lights. Now, if we are having a red light falling on a red surface, what's going to happen is the intersection of SED of the red light with the red surface is going to be reflected off. Meaning, for example, so if my surface has this SED and this red light is, let's say, more pure red, or let's say the falling light is having this SED and the object is actually pure red. So when the object is going to reflect, it can't reflect these colors. It's not going to reflect any of these colors, only going to reflect this portion. So when this light is falling on this surface, so the red portion will be reflected. The other portion, this portion of the light, will be absorbed. So only the surface only reflect the colors, specific colors related to its color, and it's going to absorb any color that doesn't match its SAD. So in here we can see a more clear example of the absorption. So for example, if you have a blue light, now let's say the blue light is not a pure blue light. Let's say it's a mix of colors. So it's blue with a little red, a little green. So the blue part will be absorbed. It's not going to be because reflected of the red surface. Now, if there's like a slight part of that blue light which is red, this color is going to be reflected off. Now, how are you going to see the red surface? When you look at the red surface, you're not going to look at it, you're not going to see it as red. You're going to actually see it as more black, because when you absorb the light, it's going to look black. Only a small portion will be reflected off, so it's going to be like more reddish black. So this is what we experience, for example, in here. This is a red car at night, and this is a red car during the day. So during the day, the white light is falling on the red car, so exactly all the light is going to be reflected off. So the reflectance of that car is going to be in the red area, so this part will be reflected off. Now at night, this is what should be reflected, but the falling light on it is actually from the street light, so this is the light falling on it. So what's going to be reflected off is actually going to be the reflectance of the car, original reflectance of the color of the car, this one, and the light source falling on. So it's going to be the intersection of this light and this one in this diagram. So as we can see in here, this is actually a combination intersection of both of these diagrams. So this is the falling light, and this is the color of the car, and this is what we see, the intersection of both. So as we can see, what we are going to see is a little green, a little yellow, although it was supposed to be more of the red part in here. But because the light falling on it didn't have much light in the red part, so what you actually see is a portion of the red, a little red, and actually a portion of the green, yellow, and blue, which is going to look like brown. Now, this is more about the importance of color and how of light and how we should be careful about that. For example, these are more for interior designers. So, for example, if you have a supermarket, so to make the vegetables, the red vegetables or the red meat to look fresh, the light has to show all the parts of the spectrum of the red color. So for example, here this is a comparison between two light effects on the strawberry. So this strawberry looks more fresh, although it's the same strawberry. As we can see in this image in here, some of the red light is not being reflected off, so it's gonna look more pale. It doesn't look fresh. And the same thing applies for meat. Now, we need to be careful. We are specifying light, for example. This light, as we can see in here, this is not doesn't include any red light. And also the white light lamps, they don't always have like a big portion of the red light being reflected off. So we need to be careful. So if I want to illuminate something red, I need to make sure that the red part of their SED is actually high enough to reflect all the red color, all the red light of the surface. Now the same thing applies for transmittance. So this is the transmission of light. The same thing, for example, this is like a tinted glass. So same thing, if you have a blue tinted glass, if you pass a white light from one side, what you're going to see from the other side is the blue light only. So what's going to happen is the glass is going to select according to its color. It's going to select what light will it absorb and what light will it reflect. So a blue, for example, glass will actually absorb all the other lights and only transmit the blue light. And as we can see in this example here, this is a red glass. So this is illumination. This is the white light of the sun. So it's going to transmit through the glass. Now the glass is going to absorb all the light and it's going to transmit majorly the red part, as we can see in here. This is the transmitted light. This is a comparison of different types of light. So this is the north sky coming majorly in the blue range. This is the incandescent light. This is the normal lamp we used to use a long time ago. So it's more on the warm range, like yellow, reddish range. The fluorescent light is a mixture of colors. It's almost green and other colors, so it's almost like bluish green. The same thing for the compact fluorescent light, which is almost warmer, more like brownish maybe. So as we can see, we can't always use the SAD to describe a light. Sometimes we need a more easier way to describe the color temperature of light or the color of light. So we have two basic systems or two basic scales. We have something called the CCT scale and we have something called the CRI. Now the CCT is actually the correlated color temperature. So it's related to the temperature. They relate the temperature to the color, and we'll have a look at it now. And we have something else which is more simple scale. It's called the CRI. Is the color rendition index. Now let's have a look at the CCT. Now probably, so as I told you, CCT is abbreviation for correlated color temperature. So as we can see in here, now each temperature, it represents a certain color range. For example, they range from 2700 kelvins up to 7000 kelvins. Now, where did this scale come from? So probably you've learned before when you heat the materials in physics. So or chemistry actually, when you heat the material, sometimes these materials will emit off certain lights. So when you first heat, for example, first heat it, the first thing is gonna glow is red. Then when you heat it more, you're gonna get the white color coming off, emitted. Then when you heat it even more, you're gonna get a blue light. So this is where it came from, that like they related each light with its temperature. So, as you learned earlier, probably in the visualization programs like 3D Max, when you were specifying a light source, so you could sometimes change its property by, or change the color of the light by changing the temperature instead of like adding color. So, as you probably used it or remember that the color for white light was almost 4000 kelvins. So it gave you like a nice white light. If you wanted to have a warmer light, it was a less number, more like 3000 kelvins. If you wanted to have a more cool light, it was more like 5000 kelvins or even more. So in general, the CCT scale just describes the warmness or coolness of a light source. So this is the scale. Uh, as we can see, it's according to the temperature of the light. So this sunrise is 2000, so it's more on the warm range, on the like yellowish range. Daylight, the white daylight is actually 4000. Cool white is 4500. Warm white is 3500. Now these are like white and like a hues of white. Now the overcast sky, which is the cloudy sky, and we said earlier that it's more bluish, so it's 6000 kelvins. Now if we want to have a blue sky, a very blue sky, now its Kelvin is 10,000 or even more. Now let's see the effect of these, like for example, we have different lights, each one of them with described its color temperature is described with the scale. So we have the first light, it has 2700 kelvins color temperature, and the second one is 3500 kelvins, and the third one is 6500 kelvins. As you can see, for SS, you probably prefer this one or that one to this one. So this one looks more cool. This is probably because these colors, because they or go to the range of the warm color or the orange range, which like matches the complexion of our of the human face, which is more like in the brownish area. So these one will like add up to our complexion and make the face look nicer. So that's why if you want to take photography or you take photos of human faces or you want to like and illuminate an area where people interact with each other and see these like only like have interactions without like having any activities. So this range is actually more suitable. So unless you want to have an activity in a space where you have to actually see your surface or your working surface and you see exactly what colors you are dealing with, then you have to work with a more white colored uh, type of light, which is going to be range almost like 4000 kelvins. Now, the other color temperature scale is the CRI. As I told you earlier, the CRI is the abbreviation for Color Rendering Index. So, Color Rendering Index is actually using like an index, an ideal color, white color as your index. Then you are relating your light source in relation to that ideal light. So, our ideal light definitely is the white light of the sunlight, as we can see in here. CRI of 100, this is the perfect one, a perfect match for value of daylight. Now then we're going to compare our source of light to that light. Now as we can see, the SED for that light is actually that one. So what happens is, for example, I have this light, this north light, and this is my ideal light. I gave it an index of 100. So what do you think the CRI for the northern light? The CRI for the northern light is going to be including how much light is being included, how much light of this one is actually found in here. For example, most of the blue light is there. So we're going to get these ones are fine. But as we can see, the intensity of these colors is less. So probably the intensity is less by 5% probably. Let's give it like this value. So as we can see, it's covering all this light, but with this portion being reduced. So this portion will make it decrease it from 100 probably to a 95 or a 90. So this one will have a value of 90, for example, CRI. So as we can see, it's just comparing your light source to your daylight source according to how much of the white light is being covered. So, for example, the more being uncovered, the more the worse the light will look like, and the worse like colors will be missing. For example, here we have a comparison. So this is a 95, a 97 CRI, and this is a 90, this is an 80, and this is a 70. So as we can see in here, some of the light is missing in here. I think it's more on the reddish range. Also in here, it's even more on the reddish range. It's more like bluish. It's becoming, and also in here, like most of the light is missing. So if you compare this one to this one, we can see like this one will look almost pink or purple, but it should be red. So the CRI just describes the percentage of light in regards to the value of daylight light. So in general, when we're designing, we should specify a light of 90 CRI or above. As we can see here, CRI of 90 is actually quite good. If you use, you have to use CRI above 90 when color is very important, and 80 as much as possible, above 80 as much as possible to have a good color rendition. Now, 70 is not always acceptable, it is sometimes acceptable. 60 is always bad. Now we can see the effect of the CRIs on this picture in here. So this is a CRI of 80, 86 probably. So the color complexion is actually fine so far. Now it's 788. See how bad the colors look? And 62 now, like much of the red color is actually missing in here. And also the blue part. Now, if you want to compare like different lamps and different colors of different lamps, what you can do is actually you can compare these different light sources by having this type of model where you put a partition between each light and you use the same image, like try as much as possible to use an image where you have most of the colors in it. And you can see the effect of light on this image as we can see in here. So this is an example of a shop of light where they are showing the color rendition of each light. And here's the description. These are general rules for choosing white light sources. So let's have a look at each one of them. So as we can see, if you need to have a perfect judgment of colors, you need to have a full spectrum white light, which is usually the natural daylight. Uh, and as we said earlier, that we are, as humans, we prefer the white light that ranges between 3000 Kelvin up to 4100 Kelvins. That doesn't look cool nor warm. And warmer colors are usually preferred to illuminate the skin tones so they can complement skin tones. And cooler colors are preferred when we need high light levels and in hot climates. Now we think they say they are needed in hot climates because usually they give you a cooling effect, a psychologically cooling effect. Also, as we said earlier, that the color of an object is not determined by the actual color of the object. It can also it's being modified according to the like color rendition of the light falling on. So, if, for example, if I have a red apple, if the light doesn't consist much of the red light in it, it's not the apple is not going to look red enough. So you need to be careful which type of light you're illuminating your objects with and if they are matching in their colors. So now let's talk about vision. So which is important to understand so we can understand how the human eye will perceive the light around it. So what we need to know, we don't need to know much into detail, what just we need to know is that the light enters through the eye through the pupil. The pupil sometimes like dilate, like opens or closes according to the brightness ratios outside. So this is where we can see that like how the luminance is being affected and brightness is being affected. So this is why sometimes we have like a certain level of luminance, but the eye is adapted to a high level of luminance. So it's gonna close slightly, which is gonna affect the brightness level or luminance level. Okay, and at the back of the eye, we have cells that like they're called corner rods. We don't need to know them specifically, but what just we need to know is that the eye has certain cells at the center that like know like they can interpret only the colors and around it like further from the center like they can interpret only an emotion or a slight detail. So this is why like only the center or the center line of the vision is always detailed with colors and details, and if you go further like at a further angle you are just can only detect like emotion or a blurred vision around it, but the color is not going to be that much accurate. So vision is the ability to gain information through the light entering the eye. Perception is actually how the brain interpreting what it's going to see. So vision, we have information, the luminance is actually entering. the eye, but how the brain interpreting the light entering the eye and getting to these cells is what we actually is being affected. So we need to understand how the human eye will perceive the light around it so we can understand how we have to design later on for quality lighting. Because at the end, we're not going to design for numbers of light, we're going to design for what the human eye will perceive so we can ensure the quality. Now, like we said earlier, like there are two things that actually affect uh, the luminance level. So let's recall them now, which were here. So as we can see, the perception of brightness is a function of the object's actual luminance. So this information is actually entering as is to the eye. Now the eye will adapt. Now this is what I was talking about. The pupil will either like dilate or close according to the brightness levels outside, and it takes time sometimes to adapt to a certain level, then the brightness of adjacent objects. So it's going to relate the object's brightness to its surroundings. So we're going to talk about adaptation of the eye for now. Now the adaptation of the eye, the thing is of the eye, it can't like take in all the brightness ratios at a time. For example, meaning, as we can see in here, the eye is only able to see effectively in a range of brightness, like you can see from all the side of your field, vision of field, if the brightness ratio just ranges from 1 to 1000 times of the in that field. Now, if that field is gonna range from 1 to up to 1 million, the eye is not going to see all the parts of that image. It's going to see a partial of that image, which is going to range that like only like let's say one like 10% of that part is going to be visible to the eye. So it's going to see the very bright areas as white, they're going to be blurred together, and the very dark areas as, for example, dark. And somehow in between is going to see like take the grayish part into the dark, or maybe the bright part into the very bright. So it can like put it into a range of 1 to 1000 of brightness. So this is where comes the eye adaptation, where the eye actually can't see all the image as is, because the eye can't adapt to all the brightness levels at once. So for example, when we go outside under the sun and you stay for a long time, then you go inside in space directly, but you're going to see the space as very dark. This is because the eye has adapted to the brightness levels outside. So it took most of the lighting outside was very bright. So the eye was adapted to the higher range of brightness. So when we got inside, the eye has actually any level, any brightness level that is just low or mid, it's going to take it as dark. That's why when you go inside, you're not going to see, not going to differentiate between the brightness levels inside. You're going to see them all as once. And vice versa. When you're inside, you go outside, you're going to see everything as very bright. This is because your eye was adapted to the inside, then it's going to take time to adapt to the outside. Now the eye adaptation to the brightness range is not linear as well. For example, as we can see, as you can remember in acoustics, also the ear wasn't like the ear sensitivity to sound wasn't linear as well. For example, as you remember that, for example, a level of lightness that was twice as bright as the other level was, for example, multiplied by 100 or multiplied by a 10. So it's instead of being like a multiple, like 10 times brighter, it's going to be, for example, twice brighter when you multiply by 10. So this is, as we can see, the commonly experienced brightness levels. So these are like, just to know the brightness levels. For example, walking in an office is just 0.3 brightness. Sidewalk in the moon is 0.0003. So you see, just dividing it by 1000, which is actually just maybe you feel it as maybe twice as less or maybe 10 times less. So this is what we meant by eye sensitivity is not linear. Now let's have a look at the vision of fields. Now, this is very important for us to know because usually you don't see all parts of a space. Just you have a centered area. So we need to take into consideration usually the vision fields. What are they? And the center of vision. What does it target? So example in here, where let's have a look at first thing the center of vision. Usually the center of vision when you are looking straight is going to be. So as we can see, it's going to be 15 degrees below the horizontal. So as we can see it in here, this is the horizontal. So when I'm sitting straight, I'm going to see, this is my center of vision, just below. This is my center of vision here, it's 15 degrees below this horizontal line. Now this center of vision, I can see clearly in everything, in color and detail in the center of vision. But that center of vision just ranges up to 2 degrees above, around like 2 degrees cone. We call this area foveal vision. So the foveal vision is the 2 degrees of the center of vision. This is where focus, color, and awareness in the field of view they are maximum. Now, as we go further, we still can see, but it's kind of like decays, like the detail decays and the color decays. So as we can see, we call this foveal surround. This area is still within the field that we can see clearly, but not as clearly as the center of vision. So this area you can see clearly the details, but maybe the colors a little bit less, like slightly blurred. Um, so this is the 30 degrees cone. Awareness is still quite high. Then as you go further, the maximum that you go further is 180 degrees, as you can see. So it's this is the maximum vision. You can't see anything above this line. Upper limit of peripheral vision is 45 plus 15, it's 60. And here is 85 total. Now let's talk about perception. Now we understood the physics of light. We understood the vision, how the light actually falls on the eye, how the eye adapts to the light. Now the last thing we're going to look at today is the perception. Now when the information of light has entered our brain, now the brain has another method to interpret. So what we see is phenomena we should be familiar with in order to later on use to have a very high quality design. So these are the main major perception phenomena in lighting. The relativity of brightness, this is what we first described as. We see the brightness of an object depending on the surrounding brightness of the object surrounding it. Now there's something called brightness constancy, color constancy. Then we have other color perception phenomena. We have something called figure background effect, Gestalt theory, and other perception phenomena. So as we can see, the most important one is the relativity of brightness. Then these two, they are like things that the brain tricks the information taken from the eye into understanding the environment. Now, before we talk about these phenomena, I'm going to talk how a long time ago, used some phenomena to enhance the architecture visually. As we can see, ancient Greeks, they realized that what they perceive is not actually as is, even in proportions. So, for example, this is an example of Parthenon. As we can see, this is the actual elevation. It's straight columns. Everything is to scale. Everything is perpendicular. Now, what they saw is when they look from a certain angle, like they can either see. This is looking at it probably from certain angles, like they can either see like the columns gonna fall on them, or maybe the columns are wider at some areas where they're not, or bulging, or tight, or thinner. So they use these phenomena. Let's have a look at each one of them and see how they treated each one of these phenomena to their favor. Now the first thing that they found that like when you look from down up into the column, you see that the column, although it's straight up, the same rate is from down to up, but you're going to see the column when you look upwards, you're going to see it as it's getting wider. This is just related to perspective views. So to avoid this, what they did is they started making the columns at the top of a smaller radius, as you can see in here. Then the second thing they found that although the column was designed as straight, they found that like the column will look as bulgy from the center. So to counteract this illusion of concavity, they designed the columns to actually bulge a little bit outwards instead, like to counterpart the concave effect of the column when you look at it. Now the column spacing and thickness differ according to brightness ratios mainly. For example, as we can see in here, if you put this column against, for example, behind it like the natural daylight, you're going to see the column as a silhouette, as a dark object, and we had something bright. Now when you do that, the column will look thinner. And vice versa, if you look at the column and there's a building behind it, as we can see in the center of the building, the column will look thicker. So what they did is, as we can see in these columns, there are columns in the middle with the building behind it, and there are columns on the side where the sky is behind it. So they wanted to make all the columns like appear the same thing and avoid this illusion. So what they did is they did the columns in the center as they looked wider, for example, of one side, and the columns on the sides of a larger radius so they can look on the same size as the ones in the middle. Now let's start talking about the phenomena of perception. Now the most important one I told you earlier about is the relativity of brightness. Now we see the brightness of an object according to the surrounding brightness. For example, in here, as we can see in this image, we have these three dots, okay, three colors. They are of the same brightness exactly, but it depends how you perceive it on where you're located. For example, I've located it in this bright area, so I can't see the yellow clearly. I can see only the dark shades. Now, when I look here, I can't see the dark shade. I can only see this one. So in here, this yellow doesn't look bright, and the surrounding looks bright. But in here, the yellow looks very bright. So as we can see, the eye always looks for relativity of brightness to its surrounding. This is another example. As we can see, this is a painting where in the middle they located this daylight. They painted it as white and everything was dark. Now this image, no matter what you illuminate it with, for example, if you put it in a dark room or you put it under the sun, you're going to see this area as bright. This is because your eye is going to compare this area to its surrounding. And no matter what you light it with, you're going to still see there's a difference in brightness between these two areas. This is another example of relativity of brightness. Now these two gray triangles are of the same color, but the thing is you place this one on the bright background and this one on the dark background. Now which one are you going to see as brighter? Definitely this one, while if you look at the colors, they're actually the same color, but this one will appear bright and this one will appear dark. Because my human eye will relate it to its surrounding brightness. This is another phenomenon, actually the same relativity of brightness. This actually applies to the car lights. For example, during the day, the car lights are actually sometimes, when you turn them on, you can't see them because you're going to relate them to the brightness of the sky, which is very bright. Now at night, because there's no light coming from the sky or the environment, the light is going to look very bright relatively, and my eyes will pick them. Now let's have a look at the second perception phenomena. Now the second perception phenomena is actually called brightness constancy. Now what do we mean by brightness constancy or color constancy? The constancy perception phenomena, what they mean is that actual brightness is actually, there's a difference. But for me, my eye will see it as constant. For example, in here, let's have a look at this wall. Now I have light coming from this window and it's falling on the side of the wall. Now my eye is actually perceiving this wall as one of the same brightness or of the same, let's say, color. So it doesn't differentiate this zone from this zone, just sees it as one wall. Now what happens is my brain actually deciphers this brightness and takes it out and just considers the whole wall as one. Okay, it's gonna understand that I have only light coming from here. That's why this area is brighter than this area. But at the end, I'm going to see it as one element. Now the same thing applies for colors. For example, in here in this image, as we can see in this image, now let's ignore the other image. If you look at this image alone, if you're actually in that area and you look at it, you're going to see the wall as pink. You're not going to see the pink hue in the image. Now, when I had to take the picture of the same building at different times of the day, then I compared them together. Now I can see that this one has a pink hue, this one has a bluish, this one has a greenish. So I couldn't tell, I wouldn't tell this hue when I'm actually at that time looking at the building at that time outside. But now when I had to compare them, okay, now I can see that they are different. Now, why I can't tell at that specific time when I'm looking at the building that I can't tell that there's a hue, for example, a red hue in here. This is because my brain actually detects that the lighting in like environment lighting is actually more on the orange side or the red side. So my brain actually removes that color and sees the image as its actual color somehow. This is where color constancy was supposed to happen. For example, if this room was like illuminated from both areas with the warm light, I'm going to see it as normal. And also, if it was illuminated with the cool light, I'm going to see it as normal. Now, because we are having two sources of light, now my brain can't detect an overall lighting hue. So it's going to see each one of them as its actual color. So this is like a fail of color constancy of the brain. Now the brain can't see them as both walls, and it's going to see this area as separate from that area because I'm using different lighting temperatures. So if I'm having this issue, I should be careful. First thing with electric lighting, I should first thing specify two lightings with the same color rendition or the same, let's say, temperature. Now, another thing I should take into consideration, for example, if I have a room with a window and some corners with, let's say, reddish light, incandescent electric light, I should be careful to locate them away from each other so my eye won't see them once at a time and like get confused. The same thing applies, for example, when I have two natural lights of the same different temperatures. For example, my north lights, we said earlier that it's more bluish than the southern, like the direct sunlight. So for this example, as we can see, they are using for the skylight, the northern light, they use the louvers in a way to enter the northern light. Then we have the other one is facing the south. Now what happens is usually when I'm using this one alone, I'm not gonna see it as blue, but because I'm putting this light in combination with this light, I'm going to see the difference when I combine them together, and my brain can't anymore decipher the color as one. And it's gonna tell the difference. Now, the other perception phenomena is color perception phenomena. We have something called color and apparent size. Also, color actually gives us a feeling that the space, either the color is like receding to us, receding from us, or actually appearing toward us. So usually warm colors, our brain will really like interpret them as like more welcoming, more coming toward us, more closer, as we can see in this image. And like the bluish green or dark gray, more like receding and like going further away from our eyes, so the room will look like larger. Now let's have a look at this image. Before we actually interpret it, let's have a look at it and like ask you to do something. I just want you to focus on this point for quite a time. Do not look away from it. Just look here and focus for example, a couple of minutes. Then look away at a white surface, and you see that you actually see the actual colors of this image. You've seen an actual image on the black surface. What you have to do actually is just focus here for quite a time, then focus here. They're going to see the image of the woman face. Now, this theory is called light and after image. Now, the thing is, when you stare at an image for too long, your eye is going to adapt to the light coming from that image. So it's going to counteract to the light coming from that image with like the color, negative color of that image. For example, I'm staring at a blue. So my eye will like get used too much of the blue. So it's going to produce at these areas, like it's going to see an image of the negative color of the blue. For example, it's orange. So when I look at it, I'm going to see in this area orange. And same thing, when I'm looking here white, the negative is black. So I'm going to see black instead. So this is what we call the, like the after image. So now how this is useful or how this is like we should take into consideration. We should take this in choosing the color in some spaces. For example, in hospitals, and more specifically surgery rooms, usually they are like the doctors are staring for too long at the blood of a patient. So the blood color is actually very bright red. So when they look for too long at the color red, what they're going to see when they look away, they're going to see colors, patches of green. They're going to see the same image they had, but in green. So to avoid that during a surgery, to like keep the doctor like in focus and avoid having any after image of the green images, they like made all their surrounding in green. So when they have an after image of green, they're not going to see it because the background is actually green. So this is gonna apply, for example, if you are staring at any drawing, any painting, or any object of any color, of like if you have that in a certain space, you have to make sure that the other walls will have of a negative color to that color. So, for example, if you want to know the negative color of any color, for example, as we've seen in our example here, it's the red color of blood. The negative color of red is green. That's why they are using the color green. Now, if you're having, for example, blue, now the negative color should be orange. Okay. Now let's talk about the another perception phenomena, which is called figure background effect. Now our human eye will like usually try as much as possible to see the most important parts of their visual field. For example, in here, like we have these louvers. Now our eye is gonna try as much as possible to ignore these louvers because they are of least importance and try to see the background, which is more important. Now the thinner the louvers are, the better the vision will be and the better the ignorance will be. Now, if the louvers are thick, they're going to obstruct actually our view, make it impossible for that to happen. Now, we have another theory that is called Gestalt theory. The Gestalt theory is like much related to familiarity. For example, in here, as we can see, we have these two elements. Now, let's ignore these two elements. Let's have a look in here. What are we going to see in here? Now, when I usually ask students what they're receiving in here, they're going to say, okay, I see a line and a dot. Or I can see, maybe they can see it as a plan, a person and a wall. Okay, they can have different interpretations to that. Now we look in here at that one. Now ignore that one. We look at that one. We're going to see it as an exclamation mark, but the point is somehow off track or off location. So this is because we are most familiar with the exclamation mark, and this is much really related to it. So I see it as an exclamation mark, but somehow with an error. I'm not going to see it as a line and a dot anymore. So this is the Gestalt theory that our brain usually is familiar with many objects, with many visuals, and we're going to try to familiarize everything it sees to something it's familiar with. For us as architects, this is actually important. For example, there was like a study that was actually done that usually we see like uh, buildings as more inviting if it's more familiar to us. For example, if the like shape of like the actual like facade of the building included windows and the door to be located in the way like like it resembles the human face, for example, eyes and the mouth, the human will see it like unconsciously as something familiar or something inviting to them. Now, there's another phenomena, which is ceiling colors and room size. Now, we first talked about the room color or the wall color and the size. Now we're going to talk about the ceiling. Now the ceiling, if it was bright, it's going to look more spacious or more farther away. Now if it's gonna be like dark, it's gonna look further, like closer to us, it's gonna look maybe smaller in size. Now the last thing is like we can create dramatic effect by like just differentiating the brightness ratios in a space regardless of the brightness levels. Meaning, for example, in this area, the light level is actually very low, but I could create a dramatic effect by like differentiating the brightness level by creating like a low brightness areas and very bright areas comparatively to the scene itself. For example, in here, the candles, there's a light, and other is there is no light at all. So I can see like high brightness ratios area and low brightness level areas. So lighting must be designed for people's perception and not for light meters. This we should take this into consideration. And this is why we overlook the perception phenomena like we need to know about when we like make decisions later on with lighting design.